In this video, we're going to investigate the building a box problem. We are going to build a box out of an 8.5 by 11 inch piece of paper. To do this, we're going to cut out 4 squares at each corner and then fold up the sides. So it's going to be an open box because it doesn't have a lid, just a bottom and 4 sides. So the dotted lines here are the lines where I'm going to fold. This large rectangle in the middle is going to be the bottom of the box, and then these 4 rectangles along the sides are going to be the sides of the box. So I would use a piece of tape and connect these 2 sides together, these 2 sides together, these 2 sides together, and these 2 sides together. So the first question says, if I'm cutting out 2-inch squares from the corners, what will the dimensions of the box be? So if these squares are 2 inches on each side, then I want to figure out what my length, width, and height are. So for my length, I'm going to look at this longer side that starts with an 11-inch piece of paper. Now, that's not going to make an 11-inch side on the box. It's only going to be this long, because it's going to be the same as this dotted line, the length of this dotted line here on the inside. So the length of the box is going to be 11 minus 4, because I'm going to subtract these 2 2-inch sections from the 11-inch length of the paper. So 11 minus 4, which is 7 inches. For the width of the box, I'm going to look at this 8.5-inch side. Now again, the paper is 8.5 inches, but the width of the box is going to be 8.5 minus 4, because I'm subtracting these 2 2-inch pieces from 8.5. So it would be 8.5 minus 4, which is 4.5 inches. And lastly, we want to know the height of the box. Well, the height of the box, once we fold this up, these 2 sides are going to connect, and the height of the box is going to be this length, which is going to be 2 inches. So whatever size cutout we use is going to form the height of the box. If we cut out a 3-inch square, the height would be 3 inches. If we cut out a 1-inch square, then the height would be 1 inch. To get the length and the width, we would multiply whatever cutout size we're using by 2 and subtract that from the dimension of the paper. So if we were using 3-inch squares, we would subtract 6. If we were using 1-inch squares, we would subtract 2. So next we want to use the dimensions to find the volume of the box. And you might remember, to find the volume, we multiply length times width times height. So for these measurements, we would be multiplying 7 times 4.5 times 2. Now you can do this on a calculator if you want to. I know that 4.5 times 2 is 9. So this is going to be 7 times 9, which is 63. And our units for volume are going to be cubic inches, because our original units were in inches. So this box would have a volume of 63 cubic inches. Now instead of using 2-inch cutouts, we're going to have x be the side length of the square cutouts. And we want to write a formula for the volume of the open top box. So I'm going to go back to my picture here and change these measurements to x. So when I'm finding my volume here, I'm going to use the same formula that I just used, length times width times height. But now I'm going to write these in terms of x. So my length is going to be 11 minus 2 times x. And my width is going to be 8.5 minus 2 times x. So whatever the cutout size is, I'm multiplying that by 2 because there's 2 of them, and subtracting that from the dimension of the paper. Now my height is going to be X inches, because whatever that cutout size is, that forms the height of the box. So to find the volume of the box, I would multiply those three things together. So v of x, I'm writing in function notation here. This means that x is the input. So v of x equals x times 11 minus 2x times 8.5 minus 2x. Now the last thing that we want to do here is make a graph of this on Desmos. And we want to know what the largest possible value for the volume of the box is. So I'm going to go to Desmos and the graphing calculator and type in my function on the left side in the box. V of x equals x times 11 minus 2x times 8.5 minus 2x. Okay, so here's my graph. So if we look at it, I'll zoom out a little bit. So it's kind of an interesting graph. It has a part where it goes up pretty sharply and then comes back down. Then it turns around and goes back up again. So we're going to look here at just the beginning part of the graph. If I think about my context here, I can see that x can't really be very big because I only have 8.5 inches here to work with. So that means that x can be at most 4.25 inches because I can't cut out more than half of this smaller side from either side of the box. So I can limit my domain here. On my x-axis, I'm going to limit it to between 0 and, we'll say 5. So now the graph is a lot easier to see. So looking at this graph, what I'm looking for is the maximum volume, and I can do a little bit of tracing here to try to figure out what that is. Looking at the peak of this point, it looks like 66.148 is the highest that the volume could be. So the box is going to get bigger in terms of volume. If I make the cutouts bigger, the box will have a higher volume until I get to a certain point, and then it'll start making a smaller volume. And that's because as I make the cutouts, the height is going to increase, but these two smaller sides are going to decrease. So the largest possible value for the volume of the box I found to be 66.148. And I'm going to copy and paste my link for my Desmos graph. Remember, to do that, we click on the Share Graph button and then click on the Copy button. That copies it, and then I can go to my Word document and paste the link in there.